Welcome. Thank you for viewing our demo on simulation of single-spool turbojet engine using SimTurbo. We are certain that you will find this demo to be very informative and instructive about gas turbine engines and control systems using SimTurbo. Upon opening SimTurbo, the disclaimer appears. SimTurbo is very safe to use. The disclaimer is intended to warn the user to not use the results of SimTurbo for any potentially unintended or unsafe applications. If the user disagrees with the disclaimer, they may close SimTurbo by clicking the red Disagree button. If the user agrees with the disclaimer, they may continue using SimTurbo by clicking the green Agree button. For this demo, we continue with the use of SimTurbo by clicking the green Agree button. The design palette opens as a cyan blue panel with pixel grid markers to aid component placement. On the left-hand side is the Tools menu. It contains a blue section at the top for selecting pre-designed gas turbine engine architecture and associated pre-designed controls. SimTurbo also provides the option of designing the engine architecture by using individual components. The engine components can be selected using the green selection box for components such as the inlet, compressor, combustor, turbine, nozzle, and etc. System loads can be selected using the tan selection box. Hydraulic components can be selected using the red selection box. Various actuators can be selected using the orange selection box. First or second order sensors and their groupers and parsers can be selected using the yellow selection box. Various control components including PIDs, mix-max selectors, limiters, comparators, lead lag components, and other components can be selected using the blue selection box. Table lookups can be selected using the purple selection box. System signal operators can be selected using the light blue box. Various sources can be selected using the pink box. Various displays can be selected using the brown box. Now, let's take a deeper look at how SimTurbo is used to connect the system components to build the architecture of the engine system and its control. The green components are the engine components. The ambient air enters the engine through the inlet component. The ambient conditions are represented by the small blue dot attached to the inlet. The engine inlet guides air into the engine's compressor while optimizing pressure and minimizing energy loss. Note the airflow lines are represented by the blue lines attached between the components. The compressor pressurizes the air to the highest pressure of the engine. The compressed air then enters the combustor, where it is combined with fuel, as represented by the yellow line. This combined air and fuel mixture is then ignited in the compressor to produce the highest temperature in the engine. The high-temperature combusted fuel and air mixture then enters the turbine. The turbine expands the gas mixture to produce power. This power is then transmitted to drive the compressor via the shaft. This shaft is represented as the dashed red line. The exit flow of the turbine then enters the duct where it is straightened to enter the nozzle. The nozzle converts the gas's thermal and pressure energy into kinetic energy to produce thrust. This thrust propels the aircraft. As is well known, gas turbine engines are not self-starting. Therefore, a torque starter using either electrical, pneumatic, or hydraulic power is used as represented by the square component between the compressor and turbine. This torque starter initially spins the engine to a sustainable idle speed. Near idle, the fuel PID commands fuel to the engine, and it is ignited to sustain a stable speed. The control components in SimTurbo also provide for proper monitoring of turbine temperature for proper starting, as is conducted on actual gas turbine engines. At sustainable idle conditions, the torque starter is disengaged from the shaft, connecting the compressor and turbine. Note that the characteristic parameters of each component can be modified by double-clicking on the component. The engine flows are properly modulated by the three actuators. These actuators are the fuel actuator, the nozzle actuator, and the variable stator vane actuator, which are represented by the orange components. The actuators are modulated by the control system. The control components are represented in blue. The base of the control system is 3 PID, proportional integral derivative systems. The fuel rate control is conducted by taking the minimum of the speed and turbine exhaust temperature PID systems. The output of this minimum is then limited by a fuel rate over compressor pressure limiter. The surge margin is lower bound limited to its design value using an estimator and a PID. to control the nozzle area. Note, a better, more conventional surge margin control is currently being completed for future SimTurbo releases. The variable stator vane set point is calculated as a function of compressor condition. The igniter is controlled as a function of shaft speed and turbine exit temperature to ensure that the combustor is properly lit. The signals for the necessary engine parameters are measured and transmitted to the control by the sensor components, represented in yellow. The necessary sensors include measurements of the turbine shaft speed, the compressor inlet temperature, the compressor inlet and exit temperatures, and the turbine exit temperature. In addition to the sensors are the other yellow components of groupers and parsers, which properly collect and disperse the sensor signals to the control. The surge margin set point and pilot throttle command are input into the PID controls. These set points are represented in pink. Next, let's look at the ambient tab, which provides the capability to adjust the ambient conditions. There are two modes: variable time adjustment, particularly for flight conditions of varying altitude and flight Mach number, and constant mode, which can be used to simulate test conditions at constant ambient. We can adjust the simulated altitude, flight Mach number, and delta ambient conditions. For this demo, we shall operate in variable time mode. This tab shows a table of steady-state operating conditions. In the green are the input parameters, such as ambient, engine shaft speed, design surge margin, and engine system settings, such as compressor parasitic flows, stator vane settings, nozzle settings, etc. In the blue are the calculated outputs, including combustor fuel mass flow rate, exit temperature, pressure, and flow rate for each engine component. Also calculated are the effective powers of the compressor and turbine. It is shown that the effective powers are balanced for each steady-state operating point. On the right side of the table are the calculated values for nozzle jet velocity, thermal efficiency, thrust-specific fuel consumption, net thrust, and engine pressure ratio. It is observed that as the engine speed increases, the thermal efficiency increases, thrust-specific fuel consumption decreases, and net thrust increases. Finally, we have reached a moment of truth. We select the Controls tab to examine the transient operation. The sub-tabs within Controls include the VSV setpoint, starting fuel, igniter control, each PID, surge margin estimator, fuel flow over compressor pressure limiter, and finally a sub-tab containing the time plots for each PID. We start the transient by clicking the green arrow at the top of SimTurbo. For this transient, the speed starts at 0 and temperature starts at ambient. At 4.5 seconds, the throttle commands a start, and the torque starter ramps the speed to idle. At idle, the torque starter disengages from the shaft. The PID controls take over to control the speed and limit the temperature. As noted before, in the future, a better surge margin control will be demonstrated. During the transient, we can look at different tabs showing the operation of the gas turbine engine. For example, we can look at the component tabs that show their parameters as a function of time in both printed and graphical forms. We may look at the compressor map, showing the surge margin at a comfortable design value of 15%. The combustor tab showing the combustion temperature in red and the combustor exit temperature in blue, as well as the WF over pressure value. The turbine map showing the turbine corrected flow rate and efficiency as a function of pressure ratio and corrected speed. The nozzle parameters including thrust and jet velocity. Other tabs include the cycle tab, where we can examine the Brayton cycle plots, the pressure versus specific volume plot, where the ambient condition is shown as the blue dot in the lower left corner. Then pressure significantly increases across the compressor. Then volume is expanded at nearly constant pressure due to heat addition in the combustor. Then volume expands as pressure is decreased across the turbine and nozzle. Then the gas is exhausted back to ambient conditions. Also, we may look at the sensor plots showing the different sensor voltage outputs versus parameter measurements. That concludes the demo. The creators of SimTurbo would like to thank you for your time. Please feel free to contact us and hopefully either get a free trial license or purchase a subscription or year edition or a lifetime edition of SimTurbo from the website www.simturbo.net.